and there's mw.lmd. Which instruction or instructions want to pick the output of the data cache, LMD? Yes, which instruction wants that? There's only one of them.
Load.
To load up.
So you got to go back.
Because I got to take whatever came out of the cache and shove it back into the register. All right. What registers read the Y? I mean, what instructions want this Y value?
Is it stored? Would you store it in memory?
No, store doesn't put it back in a register.
Oh, no, store don't put it back in the register. They put it in memory.
A branch doesn't put it back in the
No, it's
register.
ALU instructions.
All ALU
But they got to
instructions,
send it back to the GPR.
right? All ALU instructions, whether they're
Register
or I-type.
Yeah.
Good. What else? Load up or immediate, right? And load, and that's it, right? That's it. So what does this do on a branch?
It's either gonna send it back to the GP.
How about nothing?
Oh.
I would say, I would show for the
Doesn't do
branch.
anything.
I would say,
Right,
branch
yeah.
don't use it.
All right. So do you have a sense that every one of these little red things, we can look at the instruction register bits and maybe some other information and determine how to build them?
Yeah.
So that's what goes up in these yellow rounded rectangles. The control circuitry that generates the red signals. All right, so now we're going to do that. Are we ready?
I think.
Okay, here we go. Okay, how about PC write and branch to PC? Now, when do we write to PC? Somebody already said that.
Always.
Yeah.
Christian said.
Always. Always write it. Okay? Now, what we're going to do is, politely ignore hazards in the fetch cycle. Okay? So, in a real world, we wouldn't be able to do that. But for now, we're just going to, for this very simple pipeline data path, we're always going to write. Now, when do we assert branch to PC? Watch. It looks complicated, but it's not. When XMIR of opcode bits 4 to 2 is a 001. Look at all the opcodes.
Right.
How many of those opcodes in these three fields have 001?
The branch instructions.
Only branch instructions. So do you see that?
Yeah.
So if I look, this is bit 65432. I'm sorry, 543210. You see it? So, I'm sorry, 5432. So
from 4 to 2?
when bits 4 and 2 have the value 001,
Right.
that means that it's a branch instruction. That's the first criteria that has to be satisfied. Is it a branch?
Right.
The second criteria that has to be satisfied is
Sit up.
the condition's true.
If it's a true, it's 1, right?
Yes. So if it's a branch and the condition's true,
You branch.
then you branch. So here it is. Look. Condition goes into this AND gate, and these 3 bits. Look.
0, 0.
What do I want? I want 0,
0,
0.
1.
Well, if that's a 1, what's it here?
0.
So what if I had 0, 0, 0 there? What would the output be? 1. Because it's a NOR gate, so it's a 1. If I have a 1 anywhere here, what's the output?
True.
And therefore, what's this?
0.
0. So there it is. There's the logic circuitry that implements the branch to PC control signal.
This
You're
describes
done.
what you said, what be controlling and tell what, when you add, subtract, branch.
Well, it tells it whether or not to pick. Remember, what does branch to PC look like? It's this one. And what do I pick? Either
1 or
PC
0.
plus 4, or I either pick VTA or PC plus 4. And remember, that gets written back around into the PC. And how do I decide that? Right there. It's a very simple 3-gate piece of circuitry.
What that graph called? A 3-gate piece?
This is 3 gates. It's got a NOT gate, a NOR gate, and an AND gate. In practice, I can, an AND gate. Yeah. In practice, I could do this with one chip, a 7400 series NAND gate, because it's universal logic, but we won't get into all that. All right? So there we go. All right, what's the next one? So what does our read do?
It reads,
It reads the
the
memory, right?
right.
The data cache. Remember, it's data cache read. So, when do I do a read? Well, conceptually, when it's a load instruction, right?
Right.
But look at this.
You
How
do-
many of these opcodes have 110 in the left-hand most 3 bits?
Just load.
Just load. So there we go. When XM of IR, right, because it's in the memory stage that does its thing, right?
Mhm.
So if XM of IR, if the opcode fields 5 through 3 contain this, then assert D-read, and data cache gets read.
Oh, okay, so it used the opcode. Where used the func code?
Well, we'll get to the func code later.
But this is where.
Right now, we're able to do it from the opcode. Okay, by the way, when do I pick M to R? The same thing.
When in between 5 and
It's a load
3.
instruction.
Yeah, okay.
In this case, I look in the MW copy of IR. So when MW of IR of opcode 5 to 3. So in the memory cycle, it does the read, and then in the write back cycle, it picks LMD. Do you see it?
I see it.
What does this do?
It
Assert
reads the
read on the
data.
data cache. What does this do?
It starts.
Picks LMD and routes it back.
So, Dr. Moore, I don't hate to actually repeat yourself. LMD is,
Load memory data.
it's the only thing it's gonna do is just load the memory. It does nothing else.
It takes the output of the data cache and stores it.
That's it.
That's it.
Okay.
All right? So are we cool? And there it is. It's a pretty simple piece of code. What are you going to have? Look. 1, 1, 0. If it's a 1 here and here, what is it here and here?
0.
So 0, 0, 0 outputs a 1 because it's a NOR gate. Right? Simple piece of logic to implement both D-read and M to R. All right? Not complicated.
Right.
All right? And that's why we use these kinds of mappings. Now we're able to see how the machine code can actually cause the machine to behave in the way that's necessary such that the desired execution result takes place. It's pretty cool. It's pretty cool stuff. All right? Well, let's see. When do I have to write? When it's a store.
Stored up,
instruction.
yeah.
Look, there's only one of them that's got 3 left-hand 1 bits. And that's store double. Nobody else has 3 left-hand 1 bits. Right? So
Right.
that's easy. 1 and 1 and 1, bam, do the right. Which IR is it? The one that's in
Execute.
XM. Because when does the write take place?
In the
During
execution
the
memory.
cycle. So I look at that copy of the IR, the one that's in XM. There it is. Remember, this is a full 32-bit thing, and I'm only looking at the left-hand most 6 bits that correspond to the opcode. And of that, the 3 left-hand most bits added together gives me D right. Do you see there's not a lot of logic here? It's pretty simple. I mean, you can sit down with TTL circuitry on a breadboard and build this thing yourself. Okay, it's not real complicated.
But
Now,
we did that on one of the little practice sheets you gave us. We did exactly, we put in hex and we put in our code.
right, well, the reason, right, so listen to me. Hex and binary are the same thing.
Right,
It's just a more convenient way to writing binary.
Base 2, base 10.
Yes.
right.
So, hexadecimal. Hexadecimal, because every 1 hex digit is 4 binary bits. So it's simple. You don't have to think about converting hex to binary. You just expand it 4 bits or collapse it. So hex and binary are kind of the same thing. It's just a shorthand way of writing it.
Hex is the short.
Yes. All right. So let's see. So now we know how to do, now knowing how to do the D right. Let's continue. When do I select the next PC?
When opcode.
When it's a branch,
It is a branch.
right? Okay. Okay. Remember, what is next PC to A? What is that? That's that upper mux that's going into the ALU.
Exactly.
Right? And when do I pick that?
When it's the
When
branch.
it's a branch.
And there's, now be careful,
It's two of them.
yes? So in this case, it's a little more interesting, all right? Now, how do I know what compare? So first of all, how do I know it's a branch?
By them,
0, 1, all right? Now, here we go. On a compare, I pick the same 3, and then in addition, look, this bit out here, if I have these 3 bits, notice the difference. EQ is a 0, NE is a 1.
Right, that's all the difference.
That's the only difference. So if I know it's a branch, then I take this one additional bit, EQ, NE. Here we go. So I take these. Here we go, look. 0, 0, 1. That means it's a branch, right?
right.
And if it's a branch, what's it going to be here? A 1, right? So I take 1. Now, what if this is a 1? What does that mean?
It's a B and E.
It's a BNE, and therefore,
You have to use the CMP.
CMP is true,
Yeah.
okay? What if it's a 1? What if it's a EQ?
It's be a 0.
That's going to be a 0.
Right.
So I have control comp, okay? Tells me if it's equal or not equal, and then I use that in conjunction with whether in fact they're equal or not equal inside of the comparator to come up with the resulting condition. Makes sense, right? So once again now I'm able to, so what does this signal control? The upper mux into the ALU, and what does this signal control?
BEQ
The
or
comparator.
comparator.
Tells us what kind of comparison to make.
BEQ or BN.
Why can't I just use this last bit?
Because other ones got
There's
zeros
other
and
instructions that have
ones.
1s and 0s there. So I first have to,
Do the opposite.
I first have to make sure that it's a branch.
Yeah.
Makes sense, right?
Oh, that's.
Dr. Morris.
Yes.
But now that CMP,
Yes.
doesn't that use the isn't that including the condition?
No, the condition is derived based on what CMP tells it. Either compare it as equal or compare it as not equal.
Okay.
And then it looks at the relationship between the two specified registers, and we already saw how to do that. You subtract them,
Okay.
right? You subtract them. If it's 0, then you OR them all together, yada, yada, yada.
Mhm.
And then based on what this says, oh, I'm dying here, it's all right. So based on what comp says, I either do it or I don't. All right, let's move on. Now let's try to move on. All my technology just stopped. All right, here we go.
Is it moving?
It will. All right, here we go. ALU op. Whoa. ALU op's a little more of an interesting beast. All right, first of all right, let's look at the whole enchilada here. So, and here's the bottom line out to the right. All right? When do I do an add?
When the bump code.
Any immediate instruction. You see it?
Mm-hmm.
Any immediate instruction I end up adding, no matter what.
Yeah.
All right? And if it's an add instruction, I add.
Right.
All right, so it's pretty easy to decide when to add. Right? When do I and?
In a when it's an R type.
R
No,
type.
when it's a, well, ultimately yes, but when it's an and instruction. When do I or?
When it's
When it's
or
always
instruction.
When do I subtract?
With the
When it's a
subject.
subtract instruction. Otherwise, I add. Right? So now look at this. Now, there's really, I'm going to have an auxiliary control signal that determines whether it's R-type or I-type. And the reason is, if it's I-type, then no matter what,
You add.
it's an add. So if I could first determine if it's an R-type, okay, if it's not an R-type, what does it have to be? I-type. If it is an R-type, then all I have to do is look at the font code. Do you see it?
Mm-hmm.
All right. Good. So here we go. Let's move on then. And it is indeed